Yeah.
Yeah. Okay. All right. Um, all right. So, so exam 2 is going to cover the material we're doing here in chapter 4, 4.1, and then 4.3 to 4.7. And so far we've covered up to we're in the middle of 4.4. And the second exam will tentatively be scheduled for Wednesday, June 16th. So that's a week from Wednesday. Okay. Again, guys, the exams are based on the homework, simply, problems just like what you have on the homework. So that is the material that you need to study for the exam. All right. So also, for the next exam, I need everybody to have their webcams up and running. So find some time and get that up and running and working, and let's avoid what happened during the first exam where several people didn't have them up and running. I am not going to allow the exam to take place without, for those people who don't have their webcams up and running, I won't let them take the exam. Okay? It has to be up and running. And if you have internet connectivity problems, you're going to have to find a place where the connectivity is better in order to do that. All right, so at some outside source or something using your mobile phone, maybe, I don't know. So if you just simply don't have access to a better internet connection, let me know and we'll see what we can do. All right, so last time we were covering section 4.4. We went up to 176. So we're still on section 4.4, and this time 183. Okay, so problem 183 in 4.4. So the book is here. 183. All right, so for the following exercises, find the parametric equations for the normal line to the surface at the indicated point. So there's the tangent plane and now the normal line, normal meaning perpendicular. So perpendicular to the tangent plane is what perpendicular to the surface would mean at the given point. So it's not asking you to find the tangent plane, but you have to find the tangent plane in order to get the normal line, because the normal line, the slope vector, is that normal vector. So in 183, we have z is 5x squared minus 2y squared. And find the normal line at 2, 1, 18. At 2, 1, 18. Notice if you plug in x equal to 2 and y equal to 1, then you do get 18, because this will be 20 minus 2. So notice z at x equal to 1, y equal to 2 is 5 times 4 minus 2 times 1, which is 18. So that's the point of tangency. So first, find the plane. All right, first find the tangent plane. So the tangent plane is equal to z, has this equation, z minus a times the partial of z with respect to x at the point AB, x minus a, times the partial of z with respect to y at AB, times y minus b. So using the differential notation this time. Okay, so these two parameters are again the partial derivatives with respect to x and y at the point AB itself. That's a c, sorry. Z minus c, where the c is 18 here. So first thing we got to do, find those partial derivatives. Partial z with respect to x, 10x. So partial z with respect to x at 1, 2 is equal to just 10. Partial z with respect to y minus 4y. And so partial z with respect to y at the point 1, 2 is minus 8. So the tangent plane is therefore z minus 18 is equal to 10x minus 1 plus, minus 8 times y minus 2. Oops, 2, 1, not 1, 2. What did I do here? X is equal to 2, y is equal to 1. So this is 20. And at 2, 1, minus 4. So this is 20, and then minus 4. So this gives you the equation for the plane in normal form, standard form. 20, so 20x minus 4y minus z is equal to, so what do we have here? Minus 18 plus 20 minus 8. All right, so this is plus 8, that becomes minus 8, minus 20 becomes plus 20. So minus 26 plus 20 is minus 6 times 20x minus 4y minus z. So the normal vector for that plane, so here's the plane, right, with that equation. And therefore the normal vector for the plane, right, that perpendicular, well, a perpendicular vector, the length of that vector can vary, is coefficients of x, y, and z. So 20 minus 4 minus 1. So you'll notice that that's the partial derivative with respect to x, partial derivative with respect to y, right, zx, that's zy, and this is negative 1. That's always just negative 1. When you use this form to find the tangent plane, there's always a 1 coefficient for z. Well, 1 over here, negative 1 if you flip it to the other side. Right, so the normal line, right, has slope vector n equal to 20 minus 4, 1, and has point, contains the point, excuse me, 2, 1, 18. Right, so you have x, y, z equal to 2, 1, 18 plus 20t minus 4t plus t. Okay? So the tangent plane automatically gives you that normal line because the normal vector, for the plane is the normal vector for the plane is just cooked into the equation of the tangent plane. Alrighty. 184. Same problem, I guess. Find the parametric equations of the normal line of the surface at the indicated point. So with 184, you cannot solve for z. So that was that same problem from before. You can do this with the techniques that we'll learn in the next section. But for now, we just simply can't really do it. Well, I'll show you how it's done, but you know, I'm not going to ask you about this. So you can't solve for z in 184. So you can't solve for z. All right, so we can't calculate z dz dx dz dy explicitly. We can't calculate them explicitly, but we can calculate them implicitly. Right, so the equation for the surface, x squared minus 8xyz plus, what is it, y squared plus 6z squared, right, and then tangent plane plus normal line at x, y, z equal to 1, 1, 1. So notice if you put in x equal to 1, y equal to 1, z equal to 1, these three terms give you 8. And then x, y, and z are all 1, minus 8 is 0. Okay, so let's apply implicit differentiation. So let's do implicit differentiation using the differential operator partial with respect to x, right, where y is constant and z is a function of x implicitly, right? So this is just like how implicit differentiation is done in Calc 1. Right? You can do implicit differentiation in Calc 1. It's just you have this third letter here. So we're going to do implicit differentiation with respect to x, but y is a constant when we're applying the differential operator partial with respect to x to both sides of this equation. So partial with respect to x, x squared minus 8xyz plus y squared plus 6z squared is partial with respect to x at 0. Right? So apply partial with respect to x. Partial with respect to x at x squared is 2x. My 2 and that symbol look disturbingly the same. So it's 2x. And now I have 8xyz. So 8y, right? 8y, we'll put the y here. 8y xz. So the 8y is a constant. And so you have x times z. So use the product rule on that. So partial with respect to x is 8yz, right? So remember the product rule, right? Product rule, the derivative with respect to x of f times g is f prime g minus g prime f, right? So we have x and z. So f prime is 1, and g is z, multiplied by 8y. And then the derivative with respect to x, where you're taking the derivative of z, is 8yx, so that's the f, and then the g prime is dz dx, right? The derivative with respect to x of z is just dz dx. Plus, what's the derivative of 6z squared, implicitly? Right, partial with respect to x of z squared, 6z squared. What's that derivative? Where z is implicitly a function of x. How does that go? Got to use the chain rule, and you do what? Oh, and then the derivative of the y squared is 0. The derivative of the 6z squared, what's that going to be? Right, you remember from Calc 1, y is implicitly a function of x, so the derivative with respect to x of y squared was what? How did that go? Right, 2y times dy dx. Derivative of the outer function times the derivative of the inner function. So that's what's going on here. So it's 12z dz dx equals 0. Leave the dz dx terms on one side. Minus 8yx plus 12z dz dx is equal to, and then the not dz dx terms, what do we got? We got 8yz plus 2x. Right, so dz dx is equal to 8yz plus 2x over minus 8yx plus 12z. Right, so that is the derivative of z with respect to x, where z is implicitly a function of x and y is a constant. So at 1, 1, 1, you have to include the z coordinate here. You're going to have 8 plus 2 over minus 8 plus 12. So that's 10 over 8. So that 8 plus 2 is 10. Did I lose a minus? I think I lost a minus sign. Hold on. Minus here. Minus. So 8 minus 2. 6 over 8. And then at the bottom, minus 8 plus 12. Oh, that's 4. So 6/4. So that's 3/2. Similarly, for the partial derivative with respect to y, we apply the differential operator. So xyz plus y squared plus 6z squared is partial with respect to y at 0. So partial with respect to y of the x squared is what? Come on, guys, we need to participate a little more than what we're doing here.
That's 0.
0. Right. This one you got to use the product rule. 8x is constant, and then you have y times z. So the derivative of the y is 1 times 8xz. And the derivative of the z, dz dy, times 8xy. Plus, what's the derivative of the y squared? Just 2y. And the derivative of the 6z squared, with respect to y is what? Just like before. Right? 12z, derivative of the outer function, times the derivative of the inner function, which is z, dz dy. So put the dz dy terms on one side and the not dz dy terms to the other side. That's 8xz minus 2y. So dz dy is equal to 8xz minus 2y over 12z minus 8xy. So it looks like I'm going to get the same thing. So dz dy at 1, 1, 1 is equal to 8 minus 2 is 6 over 12 minus 8, which is 4, so it's 3 halves again. Okay, so we found these partial derivatives using implicit differentiation. That's not something I'm going to ask you in the final about. I don't know why they're putting them in the book now, because we do that later in the next section. I mean, although the way we did it just now comes from Calc 1, I don't think that's the best problem. But there it is. So the tangent plane, z minus a, times zx at 1, 1, 1, times x, or z minus c, x minus a, plus zy at 1, 1, 1, times y minus b. All right, so z minus 1 is equal to, and these numbers are both 3 halves. A, B, and C were 1, 1, 1. So we've got 3 halves x plus 3 halves y minus z is equal to, so minus 3 halves minus this minus 3, so add 3, you get 2. So that's the tangent plane. Right, so normal vector n is equal to 3 halves minus 1. And when you use that form for the tangent plane, the z-coordinate's always minus 1. So the normal line, parametric equations of the normal line, so we're tangent at the point 1, 1, 1. So 1, 1, 1 plus 3 halves t plus 3 halves t minus t. And so there's your normal line. Okay. (184), 186. I think we've had enough for this for now. So 186, you can do that one on your own. Same setup, find the tangent plane and then the normal line. 194. 194. Okay, so this is the differential thing. So z is x e to the y. Okay, z is equal to x e to the y, and it's asking, oh no, that was 195, I'm sorry. Find the total differential function for z equals xy over x plus y, find the total differential function where x changes from 10 to 10.5 and y changes from 15 to 13. Okay, so the differential function is equal to, right? The differential function is that the change in z, dz, is equal to, del z. The change in z is approximately del z del x times delta x plus del z del y times delta y. So the change in z, okay, the tangent plane change in z is equal to partial z with respect to x, delta x, plus partial z with respect to y, delta y. The actual change in z is when you take the value of z and you tweak x and y by the delta x and delta y. Right, so in this case, so find this total differential, or what are they calling it again in this problem? Total differential. Dz, find the total differential. At x and y equal to 10 and 15. At x, y, z equal to, well, x is 10, 10, y is 15, and then the z is what you get when you plug 10 and 15 into here, so that's 150 over 25. So that is 10, 15, 6. All right, so find that total differential at 10, 15, 6. So first thing we need to do is find those partial derivatives. So partial z with respect to x. Okay, so x is the variable, y is constant. So let's use the quotient rule. Derivative of the top is what? With respect to x. The derivative of the top is just, since x is variable, y is constant.
It's just y.
Y times the bottom minus the derivative of the bottom, which is 1 plus 0, it's just 1, times the top, all over the bottom squared. So we have xy minus xy, so it's y squared over x plus y quantity squared. All right, so y over x plus y, that whole thing there, squared. So the partial z with respect to x at 10, 15 is going to be equal to, so 10 over 25 squared, so it's 2/5 squared, so that's 4, no, I'm sorry, yeah, divided by 5, that's 2/5 squared, so 4 over 25. So that's the number that goes right there. Partial z with respect to y, anyone want to guess what it's going to be? Is there any difference between z and y in this function? If you switch z and y around, what happens to the function if I exchange x and y? Do I get a new function or do I get the same thing? So I take that function, I erase the x's, and I replace with y. And then I erase the y's and replace with x. Do I get the same function back or a new function? Same function back or a new function? If I exchange x and y. Let me do something here. Suppose I exchange x and y now in this function. Do I get the same function back? Come on, guys. Well, on the
No, I
top,
think
nothing changes. If I change x and y, or exchange x and y, then the product xy goes to the product xy. But the difference x minus y goes to the difference y minus x. So it's not exactly the same function, right? It's different. It gets negated, right? But up top, but on the bottom, and because we have a plus there, it's the same. It's the same function back. So the derivative with respect to y is the same as the derivative with respect to x, exchanging x and y. So it's going to be x over x plus y, quantity squared. See, it's a symmetric function with x and y. Exchanging the roles of x and y don't change the function. So when you take in partial derivative with respect to x and partial derivative with respect to y, they're the same, except that you exchange the x's with the y's. Right, so this is y over x plus y squared. This is x over x plus y squared. Has to be. I mean, I could do it. You could do the calculation, but you'll see that that's what it's going to be. So partial z with respect to y at 10, 15. Not that this is going to be the same number, okay, because y is not equal to x numerically here. So it's 15 over 25 quantity squared. So that's 3/5 squared. So it's 9 over 25. So the total differential, del z. So you can call it del z or delta z. It's not like any big difference. So del z is partial z with respect to x. That's 4/25 delta x. It's change in x. Plus 9 over 25 delta y. So in the problem, they're asking you find the approximate. No, that's 195. I keep looking at that. Find the total differential where x changes from 10 to 10.5 and y changes from 15 to 13. So what are delta x and delta y? If x goes from 10 to 10.5 and y goes from 15 to, what was it? 13, then delta x is equal to what? How does delta x change? How does x change? It goes from 10 to 10.5. So the change in x is what? It's a half. Did we add it or subtract it? We added it. So the delta x is a half. And the delta y, well, we subtracted 2. So that's minus 2. So the total change for these values of delta x and delta y is partial with respect to z, del z, so 4/25 times a half plus 9/25 times minus 2. So that's 4 over 50 minus 18 over 25. Also 2 over 25 minus 18 over 25. So that's 16 over 25, negative 16 over 25. So it's saying that the change in z for this delta x and delta y is approximately negative 16/25. All right, this represents the approximate change in z. So it's the change in z along the tangent plane. So the change in z along the tangent plane takes z from, what was it? It was 6 to that. From 6 to 6 minus 16 over 25, which is equal to what? So 25 times 6, 150. So 150, 134 over 25, right? Which is, the new value for z along the tangent plane. Now, what is the actual change in z? What do you mean? Nothing? You want this? Go ahead. What is the actual change in z? Okay, so let me draw a picture for you what we're doing here. So you've got your surface. You've got your surface, and you've got this point of tangency right here. And on that point of tangency, you've got your tangent plane. Right, so you've got your tangent plane. And this point, that point of tangency, was 10, 15, 6. Now we're changing x by 1/2 and y by -2. So we're going 10 to 10.5 go out this way, and then for the y we're going back, so like over here. Okay, so this is x equal to, let me put it there. (10.5), 12. Right, so x equal to 10.5, y equal to 12. So we've just calculated the change on the tangent plane. Right, so given that change, right, given that change in x and y, the change in the z value along the tangent plane is the z value of that point. And the change in the z value along the surface is right here. And the point is, for tiny variations, delta x and delta y, those are about the same. Right, so we're comparing dz with the actual delta z. So the actual delta z is, well, it's z at the original point, 10, 15. I'm doing it backwards. So it's z at 10.5, 12 minus z at 10, 15. So let's actually, it's equal to 10.5 times 12 over 10.5 plus 12 minus 10 times 15 over 10 plus 15. So this is equal to 10.5 times 12 divided by 0.5 plus 12 minus 10 times 15 over 10 plus 15. Right, so that's how it interpreted what we were saying. So the result is negative 0.4, so negative fifths. right? So the actual change in z was that much, and the differential, the total change, is 16 over 25, which, so if you put this over 25, so that's, right, so if you multiply this by 5, so that's equal to minus 10 over 25, right? And then the differential dz is 16 over 25, negative 16 over 25. Okay, so that's that total differential. It approximates the change in z, and when the changes in x and y, for certain changes in x and y, it estimates the change in z. And when the changes in x and y are fairly small, right, which they're not really in this problem, the delta x is a half and delta y is 2, or negative 2, then they're almost the same thing. So they're off here by 6/25, which is not nothing. That's definitely something. It's a significant error.
Dr. Salati, quick question. The delta y is -2. And I'm not saying it's going to totally change the results, but I think it should be 10.5 times 13 over 10 as well.
Did I use the wrong number? 10 point fit to 13. I'm sorry. So where did I use the 12? I just right there. That's 13. So did I do it right in this one? Yeah, of course you don't actually plug that number in there. So 13, so that's going to make it maybe a little bit better. So minus 1.914, we'll just say. And then this one was 16 over 25, which .64, way off.
Yeah, I think it was 0.19, 0.19.
I'm sorry, what did I do? 1.1914. Okay, so it's, well, less bad. Still bad. So, well, the difference being like 0.5, right? So it's not minuscule. But then again, the delta x and delta y are big. They're not small. So when I say delta x and delta y are small, I mean like, 0.01 and 0.002 or something. What is the practical usage of that? Well, almost nothing. When you're doing estimations of functions using tangent planes and things like that, I mean, there's objects that are better than tangent planes, right? Just like in Calc 1, in Calc 2, excuse me. In Calc 1, you learn about tangent lines. And tangent lines really, they kind of stink as approximations to functions. But then you learn about these Taylor polynomials. So instead of like tangent lines, which is a Taylor polynomial of degree 1, you have Taylor polynomials of degree 2, 3, 4, whatever degree you want. And those Taylor polynomials, they get really close to the function for larger and larger intervals. Same deal here. There's analogs of Taylor polynomials for these things here. Although it's not as easy to deal with it because you got multivariable, but they're there. But theoretically, it's an important idea. All right, 194, 198. So same thing, we'll use the differential dz to, oh, okay, they're using a d, not the del. to approximate the change in z equal to this square root function as we go from 1, 1 to 1.01 and 0.97. So z is equal to the square root 4 minus x squared minus y squared. Right, so what is this surface, by the way? Right, I mean, if I rearrange it, I got x squared plus y squared plus z squared equals 4, right? That's the sphere of radius 2. So if I redo it like this, it's not the whole sphere. Which part of it is it? It's the top half of that sphere, right? All right, so we got the top half of the sphere of radius 2. And we're talking about tangency at this point, 1, 1, just like right here. All right, so x, y equal to 1, 1, and then z is equal to, well, what's z equal to? Square root 2. All right, so that's what that point there is. So we're going to calculate the total differential. Let me just, and then approximate the change in z. And I guess they're using just dz rather than this del thing. dz, dz, dz. Okay. So calculate that total differential for those, given changes of x and y. So calculate dz at 1, 1 with delta x equal to so we're going from 1 to 1.01. So from 1 to 1.01. So delta x is 0.01. Delta y, you're going from 1 to 0.97. So that's minus 0.03. So for delta x equal to 0.1 and delta y equal to minus 0.3. Okay, so we're moving 1 100ths and 3 100ths in either direction there, in the two different directions there. So here we should get a better approximation for delta z. But we'll compare. We'll compare and contrast. All right. So partial of z with respect to x. What is that? So, right, this is 4 minus x squared minus y squared to the 1/2. So derivative is 1/2. 4 minus x squared minus y squared to the negative 1/2 times the derivative of the inside with respect to x. It's just minus 2x. The derivative of the 4 is 0, and the derivative of the y squared is 0. So you just get that. So this becomes minus x over, and the derivative of z with respect to y, again, right, this function is symmetric with x and y. If I exchange x and y, I get the same function back. Right? So the derivative with respect to y, partial derivative with respect to y, is the same as the partial derivative with respect to x, just exchanging x and y. So in this case, it's minus y over. There's a lot of functions that are like that. They're kind of symmetric in both variables, right? In the two variables that you get, or for 3 variable functions, you get that every so often. Okay, so what do we got here? So now we need to calculate these at 1, 1, 1. So dz dy dx at 1, 1. So that is equal to, so 1 over, and then that's square root 2. And dz dy at 1, 1, is the same value, minus 1 over square root 2. So total differential dz is minus 1 over root 2 delta x minus 1 over root 2 delta y. So in this case, dz is equal to minus 1 over root 2 0.01 plus 1 over root 2 0.03, because that delta was negative, delta y. Right, so what do we actually get here? This is minus 1 divided by 2 to the 0.5 times 0.1 plus, so minus 2828.
Isn't it 0.0 and 0.02?
Isn't that what I put? Oh, saying it does. You can leave that out. Oh, 0. Oh, yeah. 0.0. So this should be pretty minuscule here. Yeah. Right. Of course, moving the decimal place over 1, 0.02828. Right, so that's the change in z along the tangent plane. Now, the actual change in z is delta z, which is equal to, well, what was the value here? Square root 2 minus 4 minus 1.01 squared minus 0.97 squared. Okay, so I mean actually changing x and y by the specified delta. So what do we get? Go to the 0.5 minus 4 minus 1.01. 0.97 to the 0.5. Didn't like it for some reason. What did I do? The 4 is not right. No, that is right. 4 minus. Oh, here we are. This here. There we go. So minus 0.01372. Right, so, oops. Zero 0.01372. So we're off by, a lot less here, by, 1 1/100th approximately. Well, a little bit more. So 15 thousandths, off by 15 thousandths. But I mean, that it makes the point, right? I mean, along the tangent plane, contrasted with the actual change in the function, they get closer together. And the important part theoretically is that the limit as delta x and delta y go to 0, the limit as those two things go to 0, is the difference in the limit as delta x and delta y go to 0 of dz and delta z, their difference is 0. Okay, so that's the important part, theoretically. And that is what's going to allow us to do the chain rule in the next section. All right, so that was 193, 190 something, 198. And then 209, 209 and 211. So for the following exercises, find the linear approximation of each function at the indicated point. Okay, so the linear approximation, well, I mean, it's just the tangent plane. It's just the tangent plane, except you write it in a functional form. I mean, you know, there's different ways of presenting the tangent plane, and these are all just variations on that. So, I mean, if you calculate the tangent plane, then the linearization fxy, or lxy, is just the tangent plane, you know, solved for z. So z is equal to this function for the tangent plane. So it's just finding the tangent plane again. So 209. So find the linear approximation. I.e. tangent plane for I'm just going to use the z equal to arctan x plus 2y. Right, so z, partial z with respect to x, so derivative of arctangent 1 over 1 plus x plus 2y, quantity squared times the derivative of the inside with respect to x, well, it's just 1. So this is zx. Zy is the same thing, plus the derivative of the inside with respect to y, that's just 2. So not symmetric, but almost symmetric. Right, so zx at the point of tangency, 1, 0, is going to be, in this case, half. Zx, or zy, at 1, 0. So, oops, that's a squared. So 1 plus 1, so it's 2, so it's 2 over 2. So that's 1. Right, so the tangent plane, right, z minus c is equal to zx at x minus a plus zy at y minus b. And then the linear approximation is just lxy lxy is equal to zx at x times x minus a plus zy times y minus b plus c. So you just move that c over there. I don't know why. That's just a nitpicky difference. This is presenting the tangent plane as just a plane with x, y, and z. This is presenting the tangent plane as a function in terms of x and y. I mean, you know, the difference here is essentially nothing. It's like, you know, you say tomato, I say tomato kind of thing. So whatever, in this case, we've got lxy is equal to zx, which is a half, times x minus 1, plus 1 times y minus 0, is equal to c, or plus c. What is c? It's arctangent of 1, 0. Arctangent of 1 is pi over 4. All right, so linear approximation is a half x plus y is equal to pi over 4 minus a half, or plus pi over 4 minus a half. So that's that. And then 211, it's the same thing, but for a 3-variable function. So in this case, it's not a tangent plane. It's a tangent space. It's a tangent 3-dimensional space. The geometry of the thing is not something really that you can visualize too easily. But the idea of a linearization is really the same thing. So for 211, so you have the 3-variable function w equals square root x squared plus y squared plus z squared. Find the linearization at the point 236. xyz equal to 236. And f of xyz equals 4 plus 9 plus 36. So that's what? 45 plus 4, 49. Oh, how about that? It's Pythagorean quadruple. All right, 4. So at xyz is 7. So this is symmetric in all 3 variables. So the partial derivative with respect to x, just x over, and switching around x, y, and z, permuting those give you the same function back. So if you want to take the 3 partial derivatives, they're all the same, just exchanging the roles of the variable that you're taking the derivative with respect to. All right, so they all just look like that. So wx at 236 is equal to 2 over, and then this thing here is 7. Wy at 236 is therefore 3/7, and wz at 236 is 6/7. Right, so 2/7, 3/7, 6/7. And the idea for the linearization L of a 3-variable function, so it's a 3-variable linear approximation. So that's wx x minus a plus wz x minus b plus wc x minus c plus f of x abc, which is 7 in this case. So linearization is 2/7 x minus 2 plus 3/7. Oops, that's a y. Y minus 3 plus 6/7. Z minus 6 plus 7. So, right, the linear approximation of the function at 236 is this. So if you want to estimate the value of f using its linearization for small values of delta x, delta y, delta z, like 2.01, 2.99, and 6.02 or something like that, you can use this linear approximation. So the idea algebraically, it moves up in dimension when you take one more variable, going from a 2-variable to a 3-variable function. But the geometry of it is not something that really you're going to visualize much anymore. that is a theme. Oh boy, you know what I forgot to do? I forgot to start this. That's bad. Oh no, I did start it. Ah. All right. Moving on to section 4.5 is on the chain rule. So 215. So we talked about during the lecture how we get the chain rule from this total differential that was defined in section 4.4. Right, so the notion of the tangent plane is what allows us to calculate this, to prove this chain rule thing, to calculate that formula that goes along with it. You know, which is definitely non-obvious. It's much less obvious than what it was, and for that, you know, regular chain rule and single variable calculus. So 215. So let W be a function of three variables. So W is x, y, cosine z. And x, y, and z are functions of t. So x is t, y is t squared, z is arcsine t. Right, so we have this variable tree, W, which is the function, the original function, is a function in terms of x, y, and z. X is a function of t, y is a function of t, z is a function of t. So ultimately, W is a function of t, right? So the ordinary derivative of W with respect to t exists. Right, so that's what they want us to find. Find dw dt. So find the ordinary derivative of the single variable function w with respect to its variable t. Right, but you've got this middle layer that you're going through, right? T squared arcsine t for x, y, and z. So chain rule says that dw dt is partial z with respect to x dx dt plus partial z with respect to y times dy dt plus partial z with respect to zw partial w with respect to z dz dt. So what do we get in this case? We get partial of w with respect to x, right? So x is variable, y and z are constant. So partial of w with respect to x is just what? It's just a constant times x. So the partial derivative of w is that constant, which is y cosine z, and then dx dt, which is just 1. dw dy is x cosine z, because x cosine z is constant and y is the variable. So the derivative of y is just 1 times dy dt, which is 2t. Plus dw dz, so that's minus xy sine z dz dt, so arc sine of t. Right, so that is dw dt. Now, Um, so I mean, that's one way to do it. That's using the chain rule. It is instructive if you actually take W in terms of X, Y, and Z, and then just rewrite the whole thing in terms of T. Right? And then take the derivative, dW dt, and see what you get. And you should get the same thing. With this, I mean, of course I did that during the lecture with, something that was just defined for polynomials. Right? Just, had W was a function, polynomial function, X, Y, and Z. And then X was a polynomial of T, Y is a polynomial of T, Z is a polynomial of T. I mean, the calculation is easier that way. With this one, it's different because you have to simplify the expression cosine, although it can be done. Cosine of arc sine of T. I don't know if you've seen how to do that. It's going to be too long. It's going to be cosine of arc sine of T. So arc sine of T. Right? So I mean, if this angle is arc sine of T, then sine is opposite over hypotenuse, so T over 1, so this is 1 minus T squared. So cosine of arc sine of T is equal to adjacent over hypotenuse, so it's just 1 minus T squared. I don't know if you've seen this trickery before. If you've got a trig function composed with an inverse trig function on the inside of it there, you can set up this right triangle thing, and then this cosine arc sine T turns into this algebraic expression, right? I mean, it's no longer this sort of weird composition. It's an algebraic expression. So, and then the sine of arc sine of T, which is here, sine of arc sine of T, that's just going to be T, right? And then X and Y are T. So, it's possible to do that calculation, but it's not bad, actually. It's a long thing with square roots and all that jazz, so I'm not going to do it. But you see how long it would take, right? I mean, not that you can even necessarily simplify such functions. For, general problems that you get. So it can be a tedious mess. But the chain rule makes it easier. So 217, more of the same, I'm sure here. So W, yeah, so this one, you could actually do it that way. So W is 5x, let's actually do that. So W is 5x squared plus 2y squared. There's no z there. And x is minus 3s plus t. Y is s minus 4t. So here you got your outer function w is a function of x and y. No z in this one. X is a function of t. Y is a function of t. Right, so chain rule says, so find dw dt, the ordinary dw dt, ordinary derivative. So dw dt is, by the chain rule, right, all the paths from w to t. So wxt, so that's partial w with respect to x, and then dx dt, right? It's from w to x to t. That gives you this expression. And then w to y to t, right? That's partial w with respect to y, dy dt. Oh, I'm sorry, s and t. Oops. S and t. S and t. And we're supposed to find both? Yeah. Find, so w is actually a function of s and t. So partial w with respect to x and partial w with respect to t. So partial of w with respect to t. So these become partial. Partial w, partial t, partial y, or partial x, partial y, partial t. So that's dw dt. And dw ds is the same thing, right? Just replacing the t with s. Right? That's the only difference, right? Here's t, t, t. That become s, s, s. Right? So you take all the paths from w to x, there's 2, and you get 1 to Alright, so w to x to s and w to y to s gives you these terms. Right? wx, xs, wy, ys. And then for t, you get the same thing. So, partial w with respect to t is going to be equal to partial w with respect to x is 10x. Partial x with respect to t is just 1. Plus partial w with respect to y is 4y. Partial y with respect to t is just minus 4. So that is equal to 10x minus 16y. Now, for partial of w with respect to the variable s, right, you can copy and paste this thing. The only thing that changes, right, you got partial w with respect to x, that's 10x. Partial w with respect to y, that's 4y. And now, partial x with respect to s is minus 3. Partial y with respect to s is 1. So this is equal to minus 30x plus 4y. So those are those two derivatives. Now, if you wanted to, you can put them in terms of s and t, right? Because x is minus 3s plus t, and y is s minus 4t. So let's check that out. I mean, let's do it, just for illustrative purposes. So let's translate to s and t. So partial w with respect to t is equal to 10x minus 16y. So that's 10 times minus 3s plus t minus 16 to s minus 4t. So we get minus 30s minus 16s. That's minus 46s. And then 10t plus 64. 10 plus 64 is 74. Alright, so minus 46s plus 74, or t. 10t plus 64t, 74. And then minus 30s minus 16 minus 46s. So in terms of s and t, that's dw dt. And then in terms of s and t, so this is the answer. Right, this is the answer to the question. Let's translate to s and t, just something extra. I mean, I'm not going to ask you this on the exam, but I mean, let's actually calculate these partial derivatives directly by translating to S and T, and then seeing what we get, that they're the same. So this one is minus 30 times minus 3s plus t. Plus 4 times the y is s minus 4t. So this is equal to 90s, 94s, and then minus 30t minus 16, so minus 46t. Now let's translate w into s and t, then calculate the partial derivative. Partial derivatives. Now let's recalculate. Partial w with respect to x and partial w with respect to t without the chain rule. Right, so w is 5x squared plus 2y squared. So this is equal to 5 times minus 3s plus t, quantity squared, plus 2 times s minus 4t, quantity squared, which is equal to 5, so what's this? 9s squared minus 6st plus t squared plus 2 times s squared minus 8st plus 16t squared. So s squared, I have 45 plus 2, so 47 s squared, and then minus 30 minus 16 st plus 32 plus 5, 37 s squared. So that's w in terms of s and t. So now partial of z with respect to s is equal to, so 47, 94 s minus 46t. Oh, what did I do? That's t squared. Minus 46t plus 0. 94s minus 46t. Same thing. Same answer as before. And then partial z with respect to t is 0. So minus 46s plus 37, 60, 74t. Same answer as before. Right? Same answers as before. Now, I mean, this second method is definitely harder to do. Right? The chain rule, it totally saves you some time in doing this calculation. Okay, so it's 217. Next problem, 220. Well, why don't we take a few minutes, 7:57. Let's come back at 8:04. Okay, so take a break. We'll come back at 8:04. Alrighty. So next problem is 220. And there's 220 and 222. Imagine they're like too much different. So 220, 222. Oh, in 222 they're asking you to do a direct substitution. But So in 220, just use the chain rule. So this is one where, you know, well, actually it's not too bad. You can do it with substitution. So fxy is x plus y, and then you have r cosine theta, r sine theta. So this is the translation to polar coordinates, right? Or to cylindrical coordinates. All right, so use the chain rule to find partial f with respect to r and partial f with respect to theta. So we have f is equal, well, is not equal, is a function in terms of x and y, and then x and y are in terms of r and theta. Right, so partial f with respect to x is partial f, or with respect to r, is partial f partial x, partial r plus partial f, partial y, partial r. So, in this case, partial f with respect to x is 1. Partial x with respect to r is just cosine theta. Plus, partial f with respect to y is just 1. And partial y with respect to r, it's just sine theta. Right. So now for the partial with respect to theta, right? In this expression here, just the r's get turned into thetas. Right? But the partial f with respect to x and the partial f with respect to y, that's the same. Those are both 1, and partial x with respect to theta is minus r. Did I have these backwards? X is r, yeah, minus r sine theta. And partial y with respect to theta is r cosine theta. Right, so partial derivatives with respect to x and y. And if you do the substitution, I mean, the substitution here is real simple. F r theta is just r cosine theta, r sine theta. And you can calculate those, you know, those partial derivatives very easily. So, another application of the chain rule. So in 222, asking you to do the same thing, you know, calculate both ways. Calculate partial f with respect to t. Sorry, not partial f. Derivative of f with respect to t, using the chain rule and using direct substitution. So, you know, rewriting this function f of x, y in terms of f of t, and then just taking the derivative, you know, with respect to t using Calc 1 techniques, and then to use the chain rule as well and compare the two. So, you know, we've already done that. I'll let you do 222 and do this on your own. $225, $229. Same thing, right? Natural log x plus y, where x and y are both e to the t. You know, calculate calculate partial derivative, calculate df dt using chain rule and using direct substitution. So well, let's do this one, why not? So f of x, y is natural log x plus y. X equals e to the t, and y equals e to the t. All right, so by the chain rule, df dt is partial f partial x dx dt plus partial f partial y dy dt. So in this case, partial f with respect to x, that's just 1 over x plus y, times derivative inside, which is just 1, times dx dt. Dx dt is e to the t. Plus df dy, same thing, is just 1 over x plus y, and then dy dt is e to the t. Right, so that's in terms of x, y, and t, but x plus y is just 2 e to the t. So in terms of t, this is e to the t over 2 e to the t, plus e to the t over 2 e to the t. All right, so this is just 1. E to the t's cancel, and it's just a half plus a half, which is 1. So now using direct substitution, all right, this was chain rule, right? F of xy, again, is natural log x plus y. So now f of t is natural log e to the t plus e to the t. So this is natural log 2 e to the t. So this is natural log 2 plus natural log e to the t. So that is natural log of 2 plus t. Right, so f prime of t, df dt, well, what is it? Derivative of natural log 2 is 0, plus derivative of t is just 1. So 1, same answer. All right, so using the chain rule and then using direct substitution. $229. So here we're looking for du dt for a specific value of t. So they're giving you a specific value of x and y. At any rate, so here we have u is equal to e to the x sine y. Where x was equal to minus natural log 2t, and y is equal to pi times t. Find du dt. So find du dt at xy equal to natural log of 2 and pi over 4. Right, so x is natural log of 2 and y is, but there's something wrong here. Um, oh, I see. So what value of t do we get here? So this corresponds to which value of t? Right, so if x is natural log of 2, so natural log of 2 is equal to minus natural log of 2t, right? So you have e to the natural log of 2 is equal to e to the minus natural log of 2t, right? So this becomes 2, and then this becomes 1 over 2t, right? So t is 1/4. Right, same thing here, right? T is 1/4, and pi t is 1/4 t. So find du dt at t equal to 1/4, or find du dt at natural log 2, comma pi over 4. All right, so du dt is partial u partial x dx dt plus partial u partial y dy dt. So partial u partial x is just the same function, e to the x sine y. Dx dt is minus 1 over t. Yeah, minus 1 over t. Right, because this is minus natural log of 2 minus natural log of t. Yeah, so the derivative is just minus 1 over t, or times, plus du dy, so that's e to the x cosine y, dy dt. dy dt is just pi. Right, so at x, y equals natural log 2 pi over 4, which is the same as t equal to 1/4, right? So plugging in all those numbers there, we get that du dt at natural log of 2 pi over 4 is equal to, so e to the natural log of 2 sine pi over 4 4 minus 4 plus e to the x again, e to the natural log of 2 cosine pi over 4 times pi. So e to the natural log of 2 is 2. Sine pi over 4 is root 2 over 2 times minus 4. Plus, again, this is 2, root 2 over 2 times pi. So we get, all together here, so root 2 times pi minus 4. Right, root 2 times pi minus 4. So we're finding du dt at this specific value of t, or du dt at the specific value of x and y. Now, if they give you the specific values of x and y, then you got to find the value of t that goes along with it, because when you use the chain rule to calculate the derivative, you get in all three variables. You get in the x, you get in the y, and get in the t. So you need to substitute in the proper values for x and y and corresponding value for t. Right? So the x and y, of course, are going to give you the t value. So that's no problem there, and you just plug those numbers in. 229. Alrighty. Just need to move on to something else here. 232. Yeah. 232. So, for the following exercises, find dy dx using partial derivatives. Okay, so in 232, we have sine x plus y plus cosine x minus y equals 4. So sine x plus y plus cosine x minus y is equal to 4. Okay, so in this one, x is the free variable and y is a function of x implicitly. All right, so find dy dx So find dy dx using partial derivatives rather than implicit differentiation. Right, so you find this dy dx using partial derivatives rather than implicit differentiation. So the way this goes is as follows, right? So here's the underpinning of it. So let f x y equal this thing here, sine x, right, where equal 4, where f x y is equal to the sine x plus y plus cosine x minus y. So now consider this tree, right? So f is a function, capital F is a function of x and y. X is the free variable, so you think of x as a function of x, as a function of itself. And y is implicitly a function of x. Yeah? Right? Capital F is a function of x and y. Right? And x is the free variable, so think of x as a function of x, and y is implicitly a function of x. Right? So via the chain rule, right, 0, which is the derivative of f with respect to x, right? So f is a function of x. So it's written as a function of x and y, but x and y are both functions of x. And it's a constant, it's 4. Well, so by the chain rule, df dx is partial f, partial x, partial x, partial x, plus partial f, partial y, dx dx, regular derivative, dx dx, dy dx. Right? This is 0. This one, partial f, partial x, dx dx is just 1. Right? That's just 1 times 1. Plus partial f, partial y, dy dx. Like that. Right? Those two known values in this right here. That's just the plain chain rule. Dx dx is 1, and df dx is 0, because it's constant, that function. All right? So as a function f, as a function of x, is just a constant. Okay, but as a function of x and y, it's not. Right? So as a function of x, it's just a constant, but as a function of x and y, it isn't. It could be, but it's not in this case. And so anyway, you solve for dy dx. So dy dx, that's the derivative that you're looking for, is just partial f partial x negated over partial f partial y. Let me write it down here. Come on now. So dy dx is partial f partial x negated over partial f partial y. That's pretty neat, right? So that partial, that implicit differentiation bit that we do in Calc 1, you know, it's not quite so elegant. But here, oh, that's pretty elegant, right? So here, right, we had this. This is capital F of x, y. Right? So dy dx is equal to partial f with respect to x negated. So that's cosine x plus y, right, times the derivative of the inside, which is just 1. That's the partial derivative with respect to x, not this implicit differentiation thing. Oh no, positive cosine. Minus sine x minus y times the derivative of the inside with respect to x is just 1. And then, of course, we're negating that whole thing. Over partial f with respect to y. So this is cosine x plus y times derivative of the inside with respect to y is just 1. And then minus, right? So minus sine x minus y, right, times the derivative of the inside with respect to y, which is negative 1. So that just becomes plus. So there it is. Right? It's really elegant. Right? This implicit differentiation thing now. So that's 232. 234, 245, 234, same deal, right? So, so 234, you've got this mixed equation of x and y, x e to the y plus y e to the x minus 2x squared y equals 0. So, right, x is variable, and then y equals f of x implicitly. Right, find dy dx. So just using that bit from before, dy dx is equal to minus partial f partial x partial f partial y, where f is just that two variable function set equal to a constant. X e to the y plus y e to the x minus 2x squared y. So dy dx is partial f with respect to x. So that's e to the y plus y e to the x minus 4xy over partial f with respect to y. So that's x e to the y plus e to the x minus 2x squared. It's 234. Same business as before. All right, 245. So z equals x, y, e to the x over y. X is r cosine theta, y is r sine theta. And so find dz dr and dz d theta, where r is 2 and theta is pi over 6. So r is 2 and theta is pi over 6, so 245. So z is equal to x, y, e to the x over y. So find dz dr and dz d theta, where r is equal to 2, theta is pi over 6. Right? But again, you need the x and y as well, because when you use that chain rule, you're going to get dz dr and dz d theta in terms of x, y, r, and theta. So which yield x equal to r cosine theta, so which is square root 3, and y equals r sine of theta, which is 1. So x is root 3, y is 1, r is 2, theta is pi over 6. Right, so we've got the function z in terms of x and y are in terms of r and theta. So, come on. So dz dr is dz dx dx dr plus dz dy dr. So dz dr is equal to dz dx. So what is that? That's going to be, so we have x times y e to the x over y. So the derivative of the x is just y e to the x. The derivative of x times y e to the x over y plus x times the derivative of y e to the x over y. So that's 1 over y times e to the xy. So those cancel. So that's e to the x over y times x plus y. Oops. Oh, I forgot the dx. Blah, blah. I forgot the dx, dr. Dx, dr is cosine theta. Plus this times sine of theta. So this is y e to the x over y cosine theta plus x e to the x over y sine theta. All right, so dz dr at the given point, 2 and pi over 6, is equal to, well, the y is 1, e to the x over y, so So root 3 e to the root 3 cosine pi over 6, which is root 3 over 2, plus x, which was root 3, e to the x over y is e to the root 3 again, sine theta, here you get 1/2. So messy, e to the root 3, well, root 3 over 2, oh, it's the same thing, isn't it? Root 3 over 2, root 3 over 2. So it's just root 3 e to the root 3. Wait, hold on. I did something wrong. Oh, I didn't do the... It's all wrong, sorry. Starting again. So dz dx, you have to use the product rule here. So you have x times y e to the x over y. So the derivative of x is just 1 times y e to the x over y. Plus x times the derivative of this with respect to x. So that's y e to the 1 over y, e to the x over y times 1 over y. So it's just e to the x over y. Times dx dr, which is cosine theta. Plus dz dy, again, or no, it's not symmetric, so this is different. So this is y times x e to the x over y. So the derivative of y with respect to y is just 1. So x e to the x over y. Plus y times the derivative of this with respect to y. So that's minus, so x times minus x over y squared e to the x over y times dy d theta, which, or dy dr, which is sine theta. So cleaning up that expression, so e to the x over y times y plus x times cosine theta, plus e to the x over y, so this is x minus x squared over y squared, sine of theta. Now plugging in all those values. So dz dr at x, y, at r theta equal to 2 pi over 6. And xy is root 3 and 1. R cosine theta and R sine theta. So e to the x over y, so that's e to the root 3. X plus y is root 3 plus 1. Cosine theta, root 3 over 2. Plus e to the root 3, x minus y, x minus x squared over y squared, so 3 root 3 minus 3, and then sine theta is half. So it's just this big messy expression here, e to the root 3 over 2. Distribute the root 3 here, so that's 3 plus root 3, plus root 3 minus 3, So those cancel, and you get 2 root 3 times the 1/2. So root 3 e to the root 3. And that's what I got before, amazingly enough. So now for the second derivative, dz d theta. Let's copy over the first 2 lines here. All right, so everything is the same, okay, except the r gets replaced by theta. So the dz dx is the same, but this changed. And the dz dy is the same, but that changed. Instead of dx dr, it's dx d theta, which is minus r sine of theta. Plus this dy d theta, so that's r cosine theta. In terms of x and y, by the way, you can put this now in terms of x and y. So the r sine theta is y, so it's minus y times y e to the x over y plus x e to the x over y, and then that's x plus x e to the x over y minus x squared over y squared e to the x over y. So dz dr at, well, the whole thing is now in terms of x, y, which is root 3 and 1. So we get minus, so that's e to the root 3. This is e to the root 3. Well, actually, you can, let's do one more line. Let's factor out the e to the root 3 along the whole thing. All right, so that's e to the x over y times minus y squared minus xy plus x squared minus x to the third over y squared. So we get e to the root 3. So minus y squared is 1, minus xy is minus root 3, plus x squared is 3, x to the third over y squared, so that's 3 root 3. So we get, this is e to the root 3 times what? So minus 3, minus 4 root 3, so 2 minus 4 root 3. So that's a messy, that's a really messy one, but anyway, there it is. Okay, so it's 8:45. So for next time, oh good, so we're getting into some nice problems next time. So for next time, we'll start doing these implicit differentiation problems. So we'll finish up those in this section, and then we'll move on to 2.6 and maybe 2.7. Okay, so for next time, all right, finish, well, not 2.5, but what is it? It's 4.5. And then start 4.6 and 4.7. So we should get through 4.6 no problem. 4.7 might take a little bit more time. All right, so watch the video lectures for 4.6 and 4.7 if you haven't already, and then let's do those implicit differentiation problems. And at the end of 4.5, and so that's starting with number like 250, 254. And we'll have one of those on the exam, like doing implicit differentiation in terms of this chain rule type calculation. Okay. All right. Have a good night, everybody, and I will see you on Wednesday.